We've seen a lot of geometric applications with integration. Area, volume, arc length, surface area, those kinds of things. Now we're going to go ahead and look at some of the more physical applications. And so this may make sense if you have taken physics before in high school, or if you're already taking Physics 1 right now concurrently. But one of the first principles that we're going to talk about is that of work. And we're going to start with one of the more basic objects, springs. So before we actually get into it, let's describe what we're talking about here. And the primary principle at work here is Hooke's law. Okay, that's Hooke with an E at the end. And what that says is that if I have a spring, okay, so let's say I have a spring here with some sort of mass attached to it, and I displace it, say, x units from its equilibrium position. So let's call this dashed line here the equilibrium position. And I displace it x meters from its equilibrium position, then the force required to stretch that spring or compress it, if I'm going the other way, is proportional to the displacement. And here K is the spring constant. Okay, it describes the stiffness of the spring. So that's the force required to stretch or compress this spring, x units from its displacement, from its equilibrium position, excuse me. Now, let's kind of get some of the units out of the way here. So the unit of force here, okay, the unit of force here is going to be in newtons if you were working in SI units, or if you are, well, the rest, if you were just the US, okay, we use pounds if we're imperial units, okay? So what does that mean now? Well, for K, that's our stiffness constant, our spring constant. Okay, the units of our spring constant is going to be in SI units. It will be, let's change back the color here, newtons per meter, or in imperial units, pounds per foot. Okay, it gives this kind of ratio, okay, this kind of proportionality constant. And then finally, the units of displacement will be, well, meters if you're in SI units, or feet if you are in imperial units. And we still have to talk about work here. Now, if you remember from Physics 1, okay, from high school, or if you're taking it now, work is equal to force times distance, but that is only in the direction that the force is applied. You can get into different cases when you're talking about, say, on an inclined plane or some sort of variable path, but the general way that we can get force here is just by, the general way we can get work is by integrating the force function. So work here, okay, is going to be the integral of our force function. Okay, and the units here are joules if we are in SI units, okay, newtons per meter. Newton meters. And if we are in imperial units, well, sadly, we just have foot pounds. Okay, so to find work, which is the change in energy in our system, we just integrate our force function. And this is how we handle it when we have springs. So let's just jump into our first problem here. So suppose it takes a force of 8 pounds to stretch a spring 6 inches from the equilibrium position. How much work is done to stretch the spring 1 foot from the equilibrium position? Well, let's just go ahead and draw a picture real quick. I'll go ahead and draw a picture of a spring here with some mass. Okay, and let's say right now that's the equilibrium position. And if I stretch it 6 inches, so let's draw it here. If I stretch 6 inches from the equilibrium position, that requires 8 pounds of force. Okay. But now, if I want to stretch it a total foot from the equilibrium position, okay, so 1 foot here, I need to find the corresponding work done to stretch the spring. So I need to find out what the force function is, then I need to find out the total energy in the system after I have stretched the spring 1 foot from the equilibrium. So let's go ahead and think about how to solve this. We want to use Hooke's law here since we have a spring. So we're going to write down Hooke's law once again. Hooke's law says that the force required to displace a spring is proportional to its displacement. Now, I know a force already, okay? This here is our force, so we have 8 pounds. I don't know my spring constant, K, that's an unknown, but I know my displacement. But be careful here. The canonical unit here, when we're using imperial units, okay, inches and feet and stuff, is, well, the foot. And 6 inches is half a foot, so we're going to put down for our displacement 0.5 feet, okay? And now all we do is solve for the spring constant, so we divide by 0.5, multiply by 2 if you want to think of it like that. Our spring constant is 16 pounds per foot. Those are the units for our spring constant here. Okay, so now we're going to take this information and create our force function for this spring, and our force function is 16 times x. Okay, that spring constant acts as our proportionality constant here. Now, how do I find the total work done to stretch the spring 1 foot from the equilibrium position? So I'm integrating here from 0, we're going to call this equilibrium position 0, to 1. Okay, so I need to find the total energy in our system, okay, over that period of distance. So the total work here, okay, we're going to integrate our force function from 0 to 1, and our force function is 16x. And this is just a simple power rule thing. We're just integrating a linear function. So we make the exponent 1 bigger, so 16x squared divided by 2. And evaluate on the boundary. Again, simple power rule thing here. We just use the fundamental theorem. So we plug in 1. Okay, well, we'll get 8 minus, well, plug in 0, we get 0. So the total amount of work done is 8 foot-pounds. That's how much energy is required to displace that spring. So a very easy application here. We find our force function. We determine the region over which we're going to integrate. Here, we're talking about from the equilibrium position. Okay, that's our 0 point. Okay, and then, boom. In general, you can kind of see that we have a familiar looking expression here for the work done for the spring, which, if you are familiar, kinetic energy. Okay, this change in energy in the system that tells you the total work done here. So now let's go into a second spring problem here. So let me go ahead and draw the spring first. Okay, there's our spring. So it takes 2 joules of work to stretch the spring from its natural length of 30 centimeters to a length of 42 centimeters, okay? So let's actually start with that one. So let me go ahead and highlight that here in this sky blue here. Natural length of 30 centimeters. What that means is that at equilibrium, the spring is 30 centimeters long. So 30 centimeters long here. Okay, we'll go that down the center there at the block of our mass here. And we're going to stretch it to 42 centimeters, okay? So if I stretch it, then this additional green distance, okay, gets it to 42 centimeters. Well, what's that difference there? Well, it's 12 centimeters. Okay, 42 minus 30 is 12 centimeters. Okay, so where that green spot is there is how much is the position of the mass after we have applied 2 joules of work. Now, the question is, let's go ahead and put that in yellow, how much work is required to stretch it from 35 centimeters to 40 centimeters? So we need to first remember that we need to think about our displacement, which is the distance, the change from the equilibrium position. So here, that's not the thing I want to do. So right here, where the block originally is, that's like our 0. And then at green here, that's like 0.12. Remember, we want to put this in meters, okay? 100 centimeters to a meter. Okay, but now 35 to 40, well, let's think about that. 35 centimeters to 40 centimeters? Well, that's 0.35 meters to 0.4 meters. Okay, but the displacement, okay, we have to subtract from the equilibrium position. So 0.35 minus 0.30, that's 0.05 centimeters. And then likewise here, 0.4 meters to, okay, whoops, let's erase. Okay, subtract that from the equilibrium, 0.1 meters. Okay, so this is our region of integration. But I don't have much to work with. I don't have a force function yet. So let's write down something that we may know, okay? We know that it takes 2 joules of work, okay? So 2 joules of work to stretch the spring from its natural length of 30 centimeters, which is our 0 position, to a length of 42 centimeters. That's 12 centimeters of displacement. So the upper limit here is 0.12. And I'm integrating a force function. Well, I don't know the force function just yet, so I'm just going to go ahead and write down a generic form of it. K times x dx, okay? That's just Hooke's law, that the force required to stretch or compress a spring is proportional to its displacement. Well, this is just power rule here, so let's go ahead and write down what we would get. So I have 2 equals, applying the power rule here, 1/2 kx squared, looks like kinetic energy, right? Evaluate this on the boundary, and of course, noting that if I plug in 0, I'll get a 0. Okay, now look at what I get here. Okay, we will get, let's put this here, 2 is equal to 1/2 times 0.12 squared times k. Well, that's an equation in k, so I can go ahead and solve it pretty easily, right? So we multiply by 2, divide by 0.12 squared, okay? So we get that k is equal to 4 over 0.12 squared. Okay, and I'll go ahead and put the units here. This is in newtons per meter. Okay, I won't go ahead and write down what the actual spring constant is just yet, just because this doesn't turn out to be a nice terminating decimal. But now we have all the information that we need. So now let's go ahead and find the total work done. So the total work here, okay, the amount of energy in our system, okay, we're going to integrate, okay, in this green region here from 0.05 to 0.1. We're going to integrate our force function here, which is k, that funny looking number there, times x squared dx. Okay, and once again, just another application of the power rule. I can go ahead and ignore that constant, okay? So I'll get 1/2 times the spring constant. Okay, and that should just be a regular x there. Okay. And then we have x squared here because of the power rule. We do our evaluation step. Okay. Anytime you're doing an integral, the process is the same for a definite integral, right? You find an antiderivative, which is what we did here, and then we're going to go ahead and plug in on the boundary, okay? So when we do the work here, no pun intended here, okay, when you do the algebraic stuff here, we get something like this, okay? Top minus bottom, just apply the FTC, that's for you and me, and you'll get something like 1.0416 joules. Okay, that's the amount of work done in this system. Okay, so pretty easy, right? What do we have to do? We needed to find the force function by some means necessary, okay, by using the data that's given to us. Okay, we integrate the force function, which gives us the total work done in the system, okay, the amount of energy in the system, the kinetic energy, if you will. And now it's just FTC, a very simple application, right? So hopefully you were able to see this very basic application of Hooke's law using integrals, okay, to find the force or work done with some springs. And in the next one, we're going to extend this to now not just talk about springs, but ropes. I'll see you in the next one.